Welcome to the second lecture of this week. In the last lecture, we have seen the general dynamical programming and general cost calculation for possibly nonlinear and non-Gaussian systems. In this lecture, we are going to concentrate ourselves on the linear Gaussian systems, and we'll develop the general control theory, optimal control theory for them using dynamic programming. So let us write optimal control of linear Gaussian stochastic systems with quadratic cost. Okay? In the last lecture, we have considered the general cost case as well. But remember, the examples that I solved was linear Gaussian systems with the quadratic costs. So here, the theory is quite general. So you can apply the theory that in those examples to nonlinear systems or non-Gaussian systems with non-quadratic costs as well. But here in this lecture, we're going to specify our system as a linear Gaussian system and our cost function as a quadratic cost function. So I have the linear system dynamic equation given as AXK plus BUK plus GWK, and YK is equal to XK. We still have perfect information. We are going to start covering the case of partial information, where we will have a measurement equation as well, where the state is not going to be exactly equal to the output, starting from the next lecture. So in the last 3 weeks of the course, we're going to consider the case with partial information. But this lecture is also related to the perfect information case. So here I'm making a simplification. These A matrix, B matrix, and G matrix can depend on time, AK, BK, GK. So here I assume that our system is time invariant, but the theory that I'm going to develop here is going to be applicable also time varying systems as well. Okay, so that ABG can depend on time, and the theory that we will develop will be equivalently valid for those systems as well. But in order to not write this case all the time here, I simplify the system to be a time invariant one. So I have here UK is equal to GK of XK. So we are looking for an optimal feedback policy. Markov feedback policy. And X0 is distributed as normal X0 with mean X0 bar and covariance sigma 0. And WK is distributed as normal WK 0 with covariance Q. And here X0, W0, W1, they are all independent. This is required for the Markov property to actually hold. We are assuming that, so in this case, X does not have to be a scalar. X can be an n-dimensional vector. And I would like to, so the XK is in Rn. And in this case, we are going to write our cost function as a quadratic cost given like this. So the cost that we would like to minimize is given as expected value k equals to 0 to n minus 1 xk transpose mk xk plus uk transpose rk uk plus xn transpose mn xn. Okay, so this is our cost function that we would like to minimize. So here these MKs and RKs are positive semi-definite matrices. Remember, these are called quadratics here, or quadratic products. And these matrices, for this function to be a ball-like function that we can minimize with respect to the inputs, we need to have MK and RK to be positive semi-definite matrices. Okay? we see that this cost function is in the following form. Expected value k from 0 to n minus 1, ck xk uk plus cn xn. Okay? And I see that here these terms are cn xn for this case is xn transpose mn xn, and ck xk UK for this specific case is that I have xk transpose mk xk plus uk transpose rk uk. Okay? We see that again, we are considering the finite horizon case, and this last cost function and last incremental cost is independent of the last input, okay? And it's given as this quadratic function, and the others are dependent on the input. So here we would like to find the optimal control, minimizing this cost function for the system. This is called linear Gaussian quadratic regulator, I can say. You might have heard the name linear quadratic regulator. It is actually the deterministic case of this problem. So if there wasn't any process noise here, then I would have the linear quadratic regulator problem. So here, if I assume that this covariance Q of the process noise is exactly equal to the zero matrix, then the process noise would be deterministically equal to 0. Okay? In that case, therefore, the problem would turn into the problem where this G, WK is exactly equal to 0 everywhere. So in that case, that means that this problem turns into the linear quadratic regulator problem when Q, covariance is exactly equal to 0. Okay? So here let us remember our theory. We are working with this optimal cost to go functions. These optimal cost to go functions, if we were in a computer engineering department and if I were teaching you this topic called Markov decision processes, it is the same topic actually, and the dynamic programming is applied in Markov decision process as well. I would call these optimal cost to go functions as the value functions. So they are called the value functions, and there is a theory related to artificial intelligence and computer engineering topics that are related to these functions. So the same topic related to the Markov chains and decision making or control of Markov chains appear also in computer engineering literature, and in that case the title of the topic turns into Markov decision processes, and control turns into decision making, and it is a topic which can be covered under the umbrella of machine intelligence or artificial intelligence. And in this case, we're also working on a topic, but with the electrical engineering notation and terminology. So we call these functions as optimal cost to go functions, and in some other theoretical areas, they are called the value functions. So V star n of xn is given as cn xn, and remember, the general theory tells us that Vk star of xk is equal to, I have minimum with respect to uk, ck xk uk, the incremental cost, plus expected value with respect to wk, vk plus 1 star f xk uk wk. And that's all. So here you see that this function f can also be dependent on time. I can write here f sub k. Okay? In that case, the system would be a time-varying system. But here, again, in this theory, I assume that the function f is independent of time, meaning that I considered only the time-invariant case. And finally, if we would like to calculate the cost, and here uk star is equal to gk star of xk, and it is the argument of the minimum uk of the same cost function here. Okay? And finally, J star, the optimal cost is given as expected value V0 star X0. And this expectation is with respect to X0. All right? So now I would like to apply this theory to this system first. The first thing that I'm going to do is to calculate the optimal cost to go for time n. Xn, the n star xn is going to be Cn xn, which is going to be this one. Xn transpose Mn times Xn. Okay? So here I can continue with calculating with Vn minus 1 star Xn minus 1. And if you do that, you're going to get something like this. Vn minus 1 star Xn minus 1 is going to be Xn minus 1 transpose. And I would have here a matrix Vn minus 1, which is different than this one, times Xn minus 1 plus a constant beta n minus 1. Okay? And if I then continue to calculate Vn minus 2 star, I'm going to get a similar function, but this constant will be different and this matrix is going to be different. Okay? So we can continue in this manner to calculate functions of this form. But you see that Vn xn is also in this form, right? Because in this case, if I try to write this function in terms of that form of functions, then I would choose Wn matrix as Mn and beta n minus 1 beta n constant as 0, because this is nothing but plus 0, the constant 0. And that means that if I do this type of computations, I would always end up with this type of function. So why not assume that we have the general case when we have Vk star of xk is equal to xk transpose. I would have wk and xk plus beta k. Okay? So I'm assuming that there is such a form of these vk star functions would be in this form. Okay? And I already see that the last function, Vn star, is in this form. Why is that? Because in this function, if I set k equals to n, then that means Wn is Mn, and beta n is equal to 0. Okay? So I see that the last function is in this form. Okay? Then if I assume that the k plus first function is in this form, then if I apply this logic here, if I apply this dynamic programming procedure, if I can show that Vk star is in this form, then I would have an induction argument, which shows that I would have always this type of optimal cost to goes in this problem. Okay? So this is going to be an assumption, and we see that it's correct for Vn star. All right? Then I will assume that Vk plus 1 star or xk plus 1 is in this form. Xk plus 1 transpose, wk plus 1, xk plus 1 plus beta k plus 1. Whatever these matrices are, I know that at time capital N, I can set Wn as Mn and beta n as 0. From this function, if I can generate Vk in the same form, then I would obtain a recursion for this Wk and beta k constants. Okay? And using that recursion, I can obtain the optimal solution, the optimal input. So if this is the form of Vk plus 1 star, then I would start calculating Vk star using this dynamic programming algorithm. So now let us compute Vk star of xk. Okay? This is minimum with respect to uk. I will first write the incremental cost at time k, which is given to us by this. Okay? Xk transpose mk times xk plus uk transpose rk uk plus I need to have the expected value plus expected value with respect to wk. I have this function, okay, as my vk plus 1 star. Okay? In this function, instead of xk plus 1, I will substitute the right-hand side of my dynamic state equation. Okay? So let us do that. Instead of xk plus 1, I would write axk plus buk plus gwk transpose. I have wk plus 1, and the same thing appears again. xk plus buk plus gwk plus beta k plus 1. Okay? So I need to minimize this right-hand side with respect to uk. Okay? But before that, I need to take this expected value with respect to the process noise wk. Know that the process noise distribution is given like this, and the process noise is independent. It's an IID sequence. Similarly, I can here make wk covariance dependent on k, so this can be qk as well. Okay? So the mean can also depend on time. But here I'm making those simplifications. I assume the process noise zero mean and the covariance independent of time. So now you see that I need to take the expectation of such a quadratic function. Expectation of beta k plus 1. Beta k plus 1 is a constant. So this constant would get outside the expectation directly. The only thing complicated that I have to do here is to take the expectation of this large quadratic function with respect to wk. So before continuing with that part, I need to give you of course some theory. So now so I know that wk is a Gaussian, and in this expectation xk and uk are deterministic variables. So this quantity axk plus buk plus gwk, it is also a Gaussian random vector. Okay? And its mean is axk plus buk, and its covariance is g times q times g transpose. Okay? So this quantity axk plus buk plus gwk, here this xk and uk are deterministic variables because this expectation is only with respect to wk. That means that I can consider xk and uk as given variables here. This is a normal distributed random variable. What is its mean? If I take the mean given xk and uk, then this part would be the mean, and the expected value of this part would be 0. Okay? So the mean is axk plus buk. And what about the covariance? Subtract the mean, so this part is subtracted, and I would only have the covariance of this part, which is gqg transpose. gqg transpose. Okay? So I need to take the expected value of a quadratic function of this variable with the matrix of the quadratic equals to wk plus 1. Okay? So how to take such an expected value? So in order to be able to understand it, I will simplify the problem a little bit. What is the expected value of X transpose sigma X? And here I'm assuming that X is normal distributed with mean X bar and the covariance sigma. It is the same problem here. This quantity is Gaussian with the mean given like this and the covariance given like this. I just give this name, I just give the name X to this, and this is sigma, and this is again X. So the mean of X is this, and covariance of X is this. I call this as X bar, and I call this as sorry, this should not be the same. So they do not have to be the same. This is the arbitrary matrix A, and the covariance of the random vector is sigma. So instead of GQG transpose, I write sigma. Instead of this mean, I write X bar. Instead of this random vector, I write X. A is WK plus 1. Okay? So how to take such an expectation? So if this was a scalar, it was easy. If X was a scalar, it was easy, right? Because if X is scalar, then A is scalar. Then this would be AX squared. And the expected value of this thing would be A times expected value X squared. Okay? And I know that expected value X squared is nothing but variance of X plus X bar squared. And the variance of X is sigma. This is sigma plus X bar squared. This is a scalar case. Okay? But we are here looking for the vector case. Okay? In that case, of course, I cannot separate this A. I cannot take it outside the expectation. Or can I? Let us now try to examine this. So this is definitely scalar. X transpose AX is a scalar. Okay? So now instead of expected value X transpose AX, I can write expected value. I know that trace of an scalar is itself. Okay? Trace is the summation of the diagonal elements, EE557. Okay? And this is the same thing. Trace of X transpose AX is equal to X transpose AX itself, because X transpose AX is a scalar. Okay? But we are going to use this trace in a very, very useful way. If you have the trace of two matrices, trace of A times B, then trace of, which means the summation of the diagonals of the matrix A times B, this is interestingly equal to trace of BA. Trace operator has this fantastic property which might be very useful in the calculation of such expected values. And actually we are going to see that we are going to be able to separate this A from the expectation by just using this trace operator. And this is equal to, because trace AB is equal to trace BA, I can take this, I can set X transpose is equal to A and AX equals to B, and I can replace their places. This is expected value, trace, and I take X transpose to the other side. And that would give me A times X transpose. Okay? Now trace is a linear operator, expectation is a linear operator, so I can interchange expectation and the trace. That is equal to trace of A is just a deterministic matrix, it can get outside the expectation, expected value X transpose. Okay? So you see that I could do the same thing that I did in the scalar case by using the trace operator. I could separate the matrix multiplication A from the expectation, and I get the equivalent form of this expression in the vector case. Now what I have to do is to calculate expected value XX transpose. And in order to be able to do that, you need to remember this. Covariance of X, a random vector X, is nothing but expected value of XX transpose minus expected value X transpose. Okay? So I see that this expectation is nothing but the covariance of X, which is sigma, plus expected value X times its transpose, which is X bar transpose. Okay? So I can write here, this is trace A, and I would have covariance, which is sigma, and I would have plus X bar transpose. So now we're very close to the result. Let us distribute these covariance multiplications here. That is equal to trace of A sigma plus trace of A X bar transpose. Okay? So now I'm going to apply the same thing that I had used here, and it was the replacement of AB with BA. So here I will take X transpose to the other side. There's nothing to do here. So trace of A sigma and plus trace of X bar transpose A X bar. Okay? This is nothing but the substitution of the mean of the random vector in the quadratic form. Okay? And I know that X bar transpose AX bar is a scalar, so I can remove the trace from here. So this is X bar transpose AX bar plus trace of A times the covariance sigma. Okay? So we get the formula here, expected value X transpose AX is equal to X bar transpose A X bar plus trace of A sigma. Okay? So we see that in order to be able to take the expected value of a quadratic form, what you have to do is first substitute the mean in the quadratic form. This is your first term plus trace of A sigma, and actually this is the variance of that term probably. So I would have here this term, trace of A sigma. All right? So that is what we are going to use here to continue our derivation. So now let us look at this Vk star xk. Okay? That is going to be, these terms are not going to change. Xk transpose Mk xk. I have forgotten the minimum, sorry. Minimize with respect to uk, xk transpose mk xk plus uk transpose rk uk plus this expected value. The expected value of beta k plus 1 is itself. I only have to take the expected value of this thing. Okay? And this is a quadratic form, and this variable has mean given like this and the covariance given like this. Okay? So I use this expression. The first thing that I do is I replace the random quantity with its mean, which is this part. Okay? Plus x bar here is this one. All right? So I have AXK plus BUK transpose, and I have, instead of A, I have here WK plus 1, and I have AXK plus BUK. This is the mean term, and I have the variance term, which is given like this, plus trace of trace of what is going to be the term here, wk plus 1 times the covariance GQG transpose. Okay? Plus there is this beta k plus 1 term here. Okay? That's very good. Okay, so now I can get rid of these. So now we got rid of the expected value. Now we need to optimize with respect to UK. Okay? And that is nothing but vector calculus. Okay? So again, I'm opening a parenthesis here. So here, if you would like to, so if U is scalar, then UK transpose. If U is scalar, so this is the scalar case, then this is RK times UK square, when UK is a scalar. When I take the derivative, then it would be, the derivative would be 2RK UK. Okay, derivative with respect to UK. What is the vector generalization of this thing? So when I have vector case, in that case UK transpose RK UK cannot be written, of course, like this. But if you use vector calculus here, and if you calculate the derivative of this scalar with respect to the vector UK, then you would get the following: 2 RK UK. It is magical. Nothing is going to change here. Okay? And this is true if RK is symmetric. If it is not symmetric, then you would have RK plus RK transpose, the symmetric component of RK. But you would always have this type of term when you take the derivative. This is a vector now. In the scalar case, this was a scalar. Okay? But here I have other type of terms. So you see that I have this type of quadratic. So I have a matrix multiplying UK here, and I have a constant term. This acts like a constant for the, with respect to the derivative with respect to UK. So here, what is the derivative of the following case? If I consider the scalar case, then I would have, let me say, I have a plus bu square r. If I have this thing, if I take the derivative of this thing with respect to u, scalar case, you know that it's 2r a plus bu times b. This is the scalar case. Okay? And in the vector case, things will get a little bit more complicated. Of course, in the scalar case, I really do not care where I put this scalar r and scalar b. This b can be here, it can be here, or I can even take it inside the summation, because b is a scalar when u is scalar. Okay? So, but in the matrix case, you have to care. So in the scalar case, I really do not care. I can write this as 2UK times r. In the scalar case, this is valid. Okay? I really do not care the place of the u and r. But in the vector case, the r should always come the first, and UK should come the second. Okay? Because otherwise the matrix vector multiplication would not make sense. All right? So here in this case, in the scalar case, I have this. And in the vector case, if you have a plus bu transpose r, a plus bu, then the derivative of this with respect to u would be the following. So I would first have 2, and I would have b transpose, in this case this is a vector or a matrix, times r times a plus bu. Okay? And you cannot change the order of these terms here in the vector case. Okay? So we know that in the scalar case, B is a scalar, so I would have B transpose is equal to B. So I can take B transpose anywhere I like. But here, no change can be done on the order of the terms. Okay? So now I can close the parentheses and continue with optimizing this thing with respect to UK. Let us take the derivative, or let me say the gradient with respect to UK. In that case, I would first take the gradient of this thing with respect to UK. It is 2RK times UK plus I need to take the gradient of this term with respect to UK, and I would use this theory here. It would be plus 2 times B transpose times this matrix WK plus 1 times this quantity itself, AXK plus BUK. Here, this AXK acts like a constant with respect to the derivative with respect to UK. Okay? So here, this A is AXK here. So this is my derivative, and because we don't have any constraints for the input whatsoever, I can equate this derivative to 0, and we'll try to find a solution for what UK is, what the optimal UK would be. So for that I will distribute this, but before that I can get rid of these 2's here. So that would give me RK UK plus B transpose WK plus 1 AXK plus I would have B transpose WK plus 1 BUK is equal to 0. Okay? Now collect all terms related to the input on one side and related to the state on the other side, then we are going to get the following. This term is related to UK, this term is related to UK. Combine these two terms, and it would give me B transpose WK plus 1B plus RK times UK. Take the state-related term to the other side, minus B transpose WK plus 1 AXK. Okay? So now I'm going to invert this matrix. Okay? I'm going to assume that this matrix is invertible, and I will calculate UK star. UK star is equal to, so I would write minus, I would have B transpose WK plus 1B plus RK. I assume this matrix to be invertible, and we can actually show that this matrix is invertible when RK is invertible, when RK is positive definite. Okay? And I would have B transpose WK plus 1 AXK. Okay? So you see that the optimal input turns out to be a linear function of the state. So we are applying linear state feedback as the optimal Markov feedback policy. Okay? Now I'm going to give this matrix multiplier of this state a specific name. Let us define this as the matrix LK. LK is the state feedback gain. Okay? It is given as B transpose WK plus 1B plus RK inverse B transpose WK plus 1A. Okay? And with this definition, UK star, which is the optimal feedback policy, GK star of XK, is given as minus LK times the state XK. Okay? So very good. So in the linear Gaussian case with quadratic cost, the optimal state feedback turns out to be linear state feedback. Okay? We measure the state because we have perfect information, and we multiply it with a gain, state feedback gain, which is dependent on time, by the way, K, and we fed it back to the input. Okay. So now I need to calculate Vk star of xk, and for that I will substitute that optimal input here into this function. Okay? Let us do that. I have already calculated the minimum. Xk transpose mk xk plus, let us substitute to optimal input. So I would have here xk transpose of the input. It is lk transpose rk lk xk plus, now instead of the state I would substitute that. So I would have a minus b lk, and this would be multiplied by xk, okay, transpose times wk plus 1 and a minus b lk xk. Very good. And finally, these remaining terms, plus trace of wk plus 1 gq g transpose plus beta k plus 1. Okay? So now let us look at this term. So I will just write the overall function once more. Xk transpose mk xk plus, we see here again xk transpose and a matrix times xk. I can actually combine these two matrices in the middle. Okay? So I can actually write this thing as mk plus, I can write it lk transpose rk lk, and I can then close the parenthesis times xk. But here I have a similar term. When I take the transpose of this term, it's going to give me xk transpose times this matrix transposed, okay, times wk plus 1 times this matrix times xk. So I can actually add this matrix in the middle to there as well. Plus a minus b lk transpose wk plus 1 a minus b lk, and I can now close the parentheses times xk plus trace of wk plus 1 gq g transpose plus beta k plus 1. Okay. So now look at the form of the function, the optimal function that we have calculated. So this is actually acting like as our WK matrix, okay? Xk transpose WK xk plus another constant, and this is going to be our constant beta k, okay? So now I can write this recursion. Wk is equal to this matrix. It is dependent on the next w, okay? So I would have this as a minus b lk transpose wk plus 1 a minus b lk, and I would have this term lk transpose rk lk plus mk, and beta k is this. Beta k is this beta k plus 1 plus a positive term here, trace, a non-negative term, wk plus 1 gq g transpose. So we have started with a function vk plus 1 of xk plus 1 in the form xk plus 1 wk plus 1 times xk plus 1 plus a constant, and then we applied our dynamic programming and we ended up with the same form of the function. With these definitions here, I would get vk star of xk as xk transpose wk xk plus beta k. So you see, and we know that the last function, Vn star, was already in this form. So then, using this theory, Vn minus 1 will be in the same form, and Vn minus 2 will be in the same form, going until V0, which is going to be in the same form. Okay? And we know how to calculate these WK matrices and beta K scalars. Okay? We know that we are going to start from Wn, which was equal to, in the cost function, Wn was Mn, and beta capital N was 0, and then I can calculate Wn minus 1, beta n minus 1, and from those I can calculate Wn minus 2, beta n minus 2, etc. recursively. Okay? So without actually repeating this procedure over and over, instead of applying this procedure, I can just calculate Wk and beta k's from Wk k plus 1 and from beta k plus 1. Okay? And then I can substitute those quantities that I find in the gain formula, and then I can substitute that into our state feedback rule. Okay? So we are going to continue in this manner to calculate, let us write V0 of X0. V0 star of X0 is going to be in the form X0 transpose W0 X0 plus beta 0, where this W0 and beta 0 will be found by a backwards recursion from time n. Okay? Using this formula. All right? And then how can I calculate the optimal cost? J star is going to be expected value of V0 star X0. And I need to take the expected value of this quadratic form and with this beta 0. Beta 0 will remain. It's going to get outside of the expectation directly. And I have to take the expectation of this thing with respect to X0. But that is really simple. It is going to be X0 bar, W0 X0 bar, plus trace of W0 times initial covariance sigma 0 plus beta 0. Okay? This is the optimal cost, and the optimal inputs UK star, they turned out to be minus LK times XK, where LK turned out to be this matrix. So I have B transpose WK plus 1 B plus RK inverse. And I would have, again, B transpose WK plus 1 A. Okay? This was the optimal feedback gain. So in this case, you might again, so we see that in the linear Gaussian system with quadratic cost functions, we have linear state feedback. And here, you can actually get the linear quadratic regulator by setting Q equals to 0 in this problem. So here we have a stochastic system, but if WK is 0 for all Ks, then I would turn this problem into a deterministic problem. Okay? Of course, if I know X0 as well. But since I'm measuring Y0, which is X0, I know X0 as well here. Okay? So here I would actually have a deterministic problem if WK is equal to 0, and that means that if Q is equal to 0, I would have an impulse function for the density of WK at 0, which means that WK is deterministically equal to 0, and the problem is going to turn into the linear quadratic problem instead of linear quadratic Gaussian, linear Gaussian quadratic problem. Okay? So when I set Q equals to 0 in these formulas, I would get the famous linear quadratic regulator, which is the optimal controller, optimal linear state feedback controller for deterministic systems, for linear systems. Okay? So now, what is going to be important for us is going to be this recursion and its properties. Okay? So now I'm going to investigate this recursion for the W matrices. And I will obtain actually a simple form. I will bring the recursion into a simpler form. So here I have just this. Let me distribute this quadratic form here. WK is equal to A transpose times WK plus 1A plus, let me say minus LK transpose B, and I have this term, WK plus 1, A minus, sorry, I'm distributing all of the terms here. So I would have A here, and the transpose of this term, A transpose, and I would have WK plus 1. WK plus 1 is a symmetric matrix, so I really do not have to take its transpose. B transpose times LK, and the last term is going to be LK transpose, B transpose, and I would have WK plus 1 and B LK. Okay? And I have this term and this term as well. Plus LK transpose RK LK plus MK. Now I will substitute LK into these formulas. So here this term is really interesting. So I see that LK transpose LK, and in the middle there is a matrix, and I have LK transpose LK. There is a matrix in the middle. There is a middle in the matrix. There is a matrix in the middle. So I'm summing these matrices in the middle. Okay. So in that case, these two terms, when they are combined, they would be giving me LK transpose times this matrix plus this matrix times LK, and I would have plus MK. So I would have here, I can combine these two terms quite easily. So let us write our terms. A transpose WK plus 1A minus, instead of LK, I write its formula, transpose of that thing. A transpose times WK plus 1 and B, and I would have that matrix inverse. B transpose WK plus 1B plus RK inverse, and the rest of the terms here. B WK plus 1A. A nice quadratic term. And then I come to this term, minus A transpose WK plus 1 B transpose. Here there is a transpose missing. Okay? That's fine. That's good. Okay? And I would have B transpose WK plus 1 B plus RK inverse B WK plus 1 A. And finally these two terms that I can combine. In those terms, I would have LK transpose. Let me write LK transpose once more. A transpose, WK plus 1, and I have B here. I'm here making a mistake. There is a mistake somewhere. Either this B transpose is not here, or that B should not be there. Let me check. I have L transpose, and when I take that, I have a B here, and in this term there is, what was that term? Let me try to see that. A minus B LK, LK transpose, B transpose. There is definitely a B transpose there. So, but here I have okay, let me continue a little bit here. So maybe I would see the mistake. LK transpose times that matrix inverse B transpose WK plus 1 B plus RK inverse, and this was the LK transpose term. Then there will come this matrix, summation of these two matrices, but it's going to be this matrix itself. B transpose WK plus 1 B RK itself, and then I would have LK itself. Okay, so this matrix inverse again, I won't write it, and I would have B transpose WK plus 1, and I would have here. Okay. So now let me try to find my stupid mistake, if I can find it. Okay, so this thing is definitely going to be B, because here I have then this B transpose. So I would have LK transpose, and then there would come B here. Okay, so then I would have here in this one there is no B here. All right. There is no B transpose here, there is just B. So this is not going to be like this, and this is going to be B transpose. Okay. So now everything looks correct, and I will add the rest of the terms, which is plus MK. All right. So now I have distributed everything here. So now let us look at these terms. So you see that here there is a matrix inverse times the matrix itself times the matrix inverse. So I will cancel one of the inverses with the matrix itself, and when you look at the remaining terms, you see that you get exactly this minus terms here. Okay, so one of these terms here is cancelling this one, and I end up just with this term, and the final term. Okay, which is very neat. So I would have the right hand side here. I can take A transpose parentheses A transpose, and I would have WK plus 1 minus WK plus 1 B transpose WK plus 1 B plus RK inverse times B transpose WK plus 1, and I can close the parentheses times A plus MK. Okay, and this is nothing but my WK. Okay. So this equation, which connects WK plus 1 to WK, has a specific name in control theory, in optimal control theory. And this equation is called Discrete-Time Algebraic Riccati equation. Okay, so this is abbreviated as DARE or DARE. Okay. So here, what is the structure of this equation? So we see that there is this MK and RK, which are time dependent in this equation. Okay. So if I think this equation as a discrete time system, its coefficients are strictly dependent on time. RK and MK are dependent on time. Furthermore, if the linear system is time varying, in that case these AK, BK, GK will be dependent, and QK would be dependent on time. So in that case, the time dependence of this dynamic equation for the matrix WK would be time varying. Okay? But the question is, suppose that this MK is not dependent on time, and suppose that RK is not dependent on time. In that case, we see that if I consider this equation as a dynamic system for the matrix WK, in that case, this would give me a stationary or linear time, not linear, but time invariant system. Okay? What would happen to the output of this time invariant system if I apply this backwards recursion over and over in time? Okay? If Rk and Mk, if they are stationary, meaning that if they don't depend on time, and if I do this recursion many times, if I apply this recursion many times to an initial condition, in that case, can we say that this Wk is going to settle to a constant value? Because we have a time invariant system in that case, and if I have a time invariant system, there is a chance that when I propagate, when I evolve the state of that time invariant system, it might actually settle at some constant value. So this Wk can go to a constant value, or can it? That is the question. So here, the answer to those questions are yes. Okay. So here, if this Rk and Mk, which are the parameters of the cost function, if they are independent of time, and if we apply this recursion over and over for a long time backwards, then this Wk actually settles at a constant value. In that case, if Wk becomes constant, and if Rk becomes constant, our feedback strategy, our feedback policy becomes a stationary policy. Okay? So that is going to be the so-called infinite horizon case. Infinite horizon case. So first of all, in the infinite horizon case, I'm going to assume that this Mk is equal to R, Mk is equal to M, and Rk is equal to R for all k. So our cost function, I'm assuming that its terms, its covariance terms are constant. So we have a stationary cost function. It doesn't change with respect to time. Stationary incremental cost function. It doesn't change with respect to time. And in that case, what we are going to do is that we are going to let n go to infinity. Okay? So if we let n go to infinity, that means that our horizon is going to get further and further away. So we're going to start this recursion in a in a distant future. Okay? And that means that in order to come to a finite time instant, this recursion will be repeated infinitely many times if I let n go to infinity. And that means that if this recursion settles to a constant covariance or constant matrix Wk, then that means that for finite time instance, we're going to get just finite W. Okay? So here is our problem. What we do here is that we have Wk plus 1 and beta k plus 1 here, and we obtain Wk and beta k from these terms. And I have here the final time instant n. Okay? I start my recursion here, and I recurse backwards, and I come until the current time instant, and then I use this matrix that I find here in my gain calculation. Okay? But then what happens if I let n go to infinity? Okay? In that case, the place where I start my iterations would become further and further, would go further and further away to the right. Okay? And in that case, for this finite time instance, this recursion will have been applied infinitely many times until we come back to the current time. Okay? And that means that if this recursion settles at some constant matrix, for the infinite horizon case, I would have a constant W matrix for finite time instance. All right? So that is that W matrix, which would be constant, is called the steady state W matrix. And the state feedback gain that is calculated by using this constant W matrix is called the steady state input feedback gain. Okay? So here, let us write these things. I shouldn't erase this. When n goes to infinity, when our horizon goes to infinity, the recursions of this form, I mean discrete-time algebraic Riccati equation, tend to converge to a stationary W bar. Under some conditions. Okay? So let me write the theorem related to this. If the pair AB is reachable, this A and B is reachable, and if the constant matrix M is positive definite, then when n goes to infinity, WK converges to W bar. Okay? Where W bar is the unique positive semi-definite solution, is the unique positive semi-definite solution of the equation we know that these W's would satisfy this discrete-time algebraic Riccati equation. If I know that the limit of WK exists, then what would happen? If WK converges to a constant, I can actually let n go to infinity in both sides of this equation, and I would replace this WK with my constant matrix W bar, and this one with W bar, this one with W bar, and this R is a constant now, okay, and this one with a W bar, and I would have plus M here, okay. So if this W converges, if this W matrix converges to a constant W bar, then that W bar matrix would be the unique positive semi-definite solution of this equation. Okay? And the theorem has a continuation. We are not going to be proving this theorem, fortunately. So I would have furthermore the matrix A minus BL bar, where L bar is the gain that is calculated using this stationary W matrix, B W bar, B transpose W bar plus R inverse B transpose W bar A is stable. In other words, the matrix, in other words, lambda I, their eigenvalues of this matrix A minus BL bar is stable. In other words, all of its eigenvalues are in the unit circle for this matrix. Okay? So when we let the horizon variable go to infinity, then we apply the algebraic Riccati equation infinitely many times, starting from infinity, to come to a finite time instant. In that case, these W variables would actually become stationary. So they converge to constants. And similarly, these betas would converge to constants. Okay? So beta cannot converge to constants, I think. So I will not consider this. I will talk about what happens to the cost function in that case. But the W's would converge to constants. Okay? And those constant matrices I call as W bar, and that W bar satisfies the stationary version or the steady state version of the discrete time algebraic Riccati equation. Okay? So actually, if I know that, and what are the conditions required for this? AB should be reachable. I need to be able to control this system. Reachability is the ability of this input to be able to control all of the modes of the system. Okay? For this stationary W bar, the sufficient conditions is that A and B should be reachable, and this M matrix in the cost function. Remember our cost function, k equals to 0 to n, and I would have xk so I have this one, plus uk plus xn transpose mn xn. Okay? So this n should be also positive definite. Okay? These are the sufficient conditions for this convergence to happen. This doesn't mean that when these sufficient conditions are not satisfied, convergence cannot happen. Okay? So when these sufficient conditions are not satisfied, then anything can happen. There might be convergence or there might not be convergence. But if these conditions are satisfied, if this input can control all of the modes of this system, this is the reachability of AB, and if this cost function, if M is positive definite, then that means that it punishes all modes of the state here. Okay? If M is not positive definite, if it has some zero eigenvalues, that means that this cost function will not punish some modes of the system. So those modes of the system can become arbitrarily large, and we wouldn't see that in the cost that we calculate. Okay? So here, the sufficient conditions are, we need to be able to control all of the modes of the system using this input, and this cost function should punish all modes of the all modes of the system. We don't want them to be large. Okay? If these conditions are satisfied, then we know that this recursion is the backwards recursion is going to converge to a constant stationary matrix. All right? And this W bar becomes the unique positive semi-definite solution of this equation. Steady state version of the discrete time algebraic Riccati equation. Okay? And we say something more. Furthermore, the matrix A minus B L bar, this matrix, where L bar is this stationary control gain here, becomes a stable matrix, which means that all of its eigenvalues are in the unit circle. Okay? What does that mean? So here, if this WK converges to this W bar, then our LK, which was given by this formula, B transpose times WK plus 1 times B plus RK inverse times B transpose, there is no K dependence on R now, and I would have WK plus 1A. If WK converges to W bar, then LK converges to L bar. Okay? L bar would become B transpose W bar B plus R inverse B transpose W bar A. Okay? So our state feedback gain also converges to a constant feedback gain. So our control becomes time invariant. All right? And in that case, our stationary control law would be UK is equal to minus L bar times XK. A stationary relationship between XK and UK. When I substitute this feedback law into my system, I would get this. XK plus 1 is equal to AXK plus B times UK is minus L bar XK plus GWK. Okay? And you see that I have A times XK and minus BL bar times XK. Then I can combine those terms. A minus BL bar XK plus GWK. So this equation, XK plus 1 is equal to A minus BL bar XK plus GWK is the closed loop state space representation. Okay? The dynamic equation for the closed loop system. And we see that this A matrix here, which I can call as the A closed loop, would be this A minus BL bar. The theorem claims that when there is such a convergence, with the steady state gain that you obtain, this closed loop A matrix of the system would become also a stable matrix. So the closed loop system would become asymptotically stable. All right? So maybe I should mention something about the cost function in this case. So here, in this cost function, if you let n go to infinity, this cost function would become infinite actually. Okay? But then how can we talk about the steady state solution? This is our J. Okay? This is our J of U0n. Okay? Or maybe U0n minus 1. This is our cost function, J U0 n minus 1. What happens when n goes to infinity? So if I try to solve this problem, if I'm trying to minimize this with respect to U0 to n minus 1 of this cost function, J U0 n minus 1, and if this is my J star, okay? Now if I let n go to infinity, limit as n goes to infinity, then this cost function, because there is no discount factor, or because there is no average term here, this cost function would go to infinity. So this optimization would give us infinite cost. Okay? So actually, calculating this cost when n goes to infinity would not be possible. Okay? And as n goes to infinity, this cost would go to infinity. Okay? So then what is this solution that we find? The solution that we find is this. Minimum u0 n minus 1, j u0 n minus 1. We don't let n go to infinity here, okay? Because it would cause a divergence of the cost function. I take the argument of this minimization, okay? And then I take the limit as n goes to infinity. Then this becomes our stationary cost functions, u0 to infinity. Okay? And in the other case, I would have u star 0 infinity would be argument of limit as n goes to infinity, minimize u0 n minus 1, j u0 n minus 1. Okay? So in our approach in this lecture, what we did was the second one. Okay? We calculated the argument of the minimization first for finite n, which was the discrete algebraic Riccati equation, and then we let n go to infinity on that solution. Okay? But if you replace the limit and the argument operations here, if you first take the limit, and if you then take the argument of the optimization, then this problem doesn't have a solution. Okay? We found, and this problem doesn't have a solution either. What we did here is that we solved the problem. We found the analytical solution for any finite n, and then we let n go to infinity. And we reached a solution in that case, okay? But if you replace this argument and the limit operations, in that case, this cost function would be infinite, and I wouldn't be able to calculate the argument of an infinite cost function. Okay? It wouldn't make much sense. Okay? So that is why we have first in this lecture found the solution of the optimization problem for an arbitrary finite n. Okay? And then we take the limit of the solution. Sometimes this is possible, and this is one of the cases. So this shows that I cannot always replace the limit and the argument operations. So let us apply this infinite horizon theory to our example. In the last lecture, we have solved two examples on the same system, and now we're going to apply the infinite horizon case to this example. So I have xk plus 1 is equal to xk plus uk plus wk, and I have yk is equal to xk. x0 is normal, x0, 1, 1. Wk is normal, w0, sorry, wk, 0, 1. And x0, w0, w1 are independent. Okay? So now we're going to find the solution for the following cost function. Expected value, I have k from 0 to infinity, xk squared plus uk squared. Sorry, I will write here n minus 1 still. This is the finite cost function, uk squared, and I would have xn to xn squared. Okay? I will find the steady state controller for the infinite horizon version of this problem. Okay? So I let n go to infinity here. So in this case, what is our stationary cost function parameters? What is mk and what is rk? Here, what I'm going to do is that I will let n go to infinity, okay? Because I'm letting n go to infinity, this last term will lose its effect because it's going to be infinitely further away from the finite value k values. Okay, so that means that I really do not have to consider this final cost function here as I let n go to infinity. Okay, because that final cost value will be infinitely further away from the finite values. So that means that I will only consider this part. This is a quadratic function, and it is 1 times xk squared. So mk is equal to 1, and rk is equal to 1 for all k. So this is my m, and this is my r for this problem. And here this part really is not important. I can put here 3xn squared, 3xn minus 4 square, etc. It really doesn't matter because I'm letting n go to infinity. It's going to get further away from the current time, infinitely further away. Okay? Now I will find this stationary w value. Okay? So let me write that equation. In this case, I will show my w bar as small w bar. Okay? This is not the mean of the process noise. In this case, that's going to show this scalar matrix here. In this case, what is B? B is 1, G is 1, okay? And A is 1. What is Q? Q in this case is 1 as well. All the quantities are 1, and the mean of x0 bar is 1, and sigma 0 is 1 as well. All right? Now let me try to solve this equation, solve the steady state version of the discrete time algebraic Riccati equation for the matrix, stationary matrix W bar. Okay? If I find the stationary W bar, then that is going to tell me what the stationary steady state feedback rule is. And it would be just this matrix, or it's going to be just a scalar. And then I can actually apply my steady state feedback. Okay? So here let me write that equation, W bar, and everything here will be a scalar, and all of them are going to be equal to 1. So A transpose is 1, A is 1. I don't really have to write it. It is W bar minus B's are 1. So I have here W bar plus 1 inverse. And I have BW bar square. B is 1. So I have W bar square divided by this inverse matrix. This is going to be a scalar. So inverse can be written as a division. So I would have W bar plus 1. Okay? And I would have an M. And M is 1 here. Okay? So the theorem predicts that equation has a unique positive semi-definite, which means in the case of a scalar, has a unique non-negative solution, and that solution is going to determine our steady state feedback gain. All right? So I would have here these terms would be cancelling. Okay, so I would have W bar square W bar plus 1 is equal to 1. So W bar square is equal to W bar plus 1. And I would have W bar square minus W bar minus 1 is equal to 0. Okay? So you see that we have a parabolic equation in this case. Therefore, we have two solutions. So what are the solutions? W bar is equal to minus B. So plus 1 plus minus the discriminant. So b squared minus 4ac, it is square root, b squared is 1 plus 4ac makes 5 divided by 2. Okay? So there are two solutions to the discrete-time algebraic Riccati equation, the stationary version, steady-state version. So I have 1 plus square root 5 over 2, and W bar is equal to 1 minus square root 5 over 2. Okay? I see that there is a unique non-negative solution. Because this solution is negative, I won't consider it. So my solution for the steady-state control law is going to be that one. And now I'm going to substitute it into the gain formula. I know that L bar is given like this. So it is going to be L bar, which is equal to B is 1, and W bar is that quantity. So 1 plus square root 5 over, maybe I should write the formula first. A is 1, I have B transpose is 1, so I have W bar here, divided by, here I would have W bar plus 1. Okay? That is my steady-state feedback gain, and all I have to do is to substitute that W bar value. So 1 plus square root 5 over 2, 1 plus square root 5 over 2 plus 1, and that is going to be 1 plus square root 5 divided by 3 plus square root 5. Okay? And this turns out to be 0.62 approximately. So my steady-state feedback law is UK star, it is G star of xk. In this case, it's a stationary feedback law because we're considering the infinite horizon case. So in this case, I have n going to infinity, and this would turn out to be minus 0.62 xk. Okay? And in this case, if I ask you to calculate the optimal cost function as n goes to infinity, if I ask you the optimal cost with this feedback law, what would that be? In that case, it's going to be infinite. Okay? So there is no finite optimal cost in this case, because we found this solution by taking the limit of the optimal solution for the finite horizon case. We did not take the limit of the cost function and found the optimal solution for that. Okay? That wouldn't be possible. Here, we found the optimal solution for any finite n, and then we took the limit of that solution as n goes to infinity. If we let n go to infinity in this cost function, the cost function would be infinite for all feedback strategies. Okay? And minimizing infinities would be difficult, if not impossible. Okay? So here, this was the example, and this completes the investigation of linear Gaussian case in the dynamical programming topic. So far, we have considered all the perfect information case. Okay? So we have considered so far only the complete information cases in this course for optimal stochastic control. What does that mean? That means that so far we always observed the state. So yk was equal to xk. So our feedback laws were were in this form. We were taking the feedback law as a function of the state. That was because we were considering the complete information case where the output is equal to xk. But in general, of course, this is not correct. In general, yk is a function of xk and the measurement noise. In that case, what to do? How to control the system? And the answer to this question is going to be given by the concept of an observer. Okay? So far, what we did was this. I have my stochastic system, xk plus 1, and I had the uk here. This is fxk, uk, wk, my stochastic system. And this was xk, and I had yk is equal to h of xk vk. So this is my output yk. So far we have assumed that we observe the state perfectly. Okay? So we removed this part and we applied state feedback g of xk, okay, to the input. All right? That is the case of complete information. But in the general case, when the output is not equal to the input itself, we have to do something else. We have to design a form of observer that would calculate or that would estimate the state of the system, and I would put here an observer, and then I would feed it back to the system. So this would give me an estimate of the state here. So that is going to be xk hat, and we will be able to feed it back via another function to the input. Okay, that is going to be called the observer concept, and of course in this case we have to estimate the state xk from its noisy observations, or in a stochastic system. And that would require us to calculate these distributions, xk given y0k. Okay? So in our next lecture, we're going to see how we can calculate such posterior distributions. And then that is going to take maybe approximately 1 week. We're going to apply our procedure to be able to find these posterior distributions to both finite state Markov chains and to both linear Gaussian systems. And we're going to learn observers for both of those systems. The observers for linear Gaussian systems is going to be called a Kalman filter. And then we are going to learn how to use that partial information that we obtain in the form of these densities in the optimal control of our stochastic system. And that is going to be covered in the last 2 weeks of this course. So we have 3 weeks left in this semester. So in the next week, I want to cover the topic of observer, and that is going to mean we will find some observers for both finite state Markov chains and for both linear Gaussian systems. And then in the next 2 weeks, we are going to cover the optimal control of these systems with partial information, meaning that the state equation will be in this form. Okay? But that's going to be all for this lecture. Thank you for watching. Bye.